Hello guys, how are you? So as you see in your email, I published a video, okay, for Thursday lecture, which talk about the one of the timers in our microcontroller, okay, and I will just go over the slides very quick. I'm assuming you saw the video, you watched the video already, but I will just go over the slides very quick for that. So let's see. So a SysTick timer is one of the timers in our microcontrollers. Okay, it is the simplest one. Okay, it's related to the system timer, the the clock frequency of the system. Okay, and how else? Yeah, as we saw, it has three. This module, this hardware module, has three registers. Okay, one is called the control register, the one that we control or configure the setup for the timer from. Okay, this register has 32 bits, although we usually concerned with only 3 bits. The enable bit should be 1 to use it. Also the clock source should be 1, which ties the system, this module to the microcontroller's clock itself. And what's called the count flag. Okay, we're gonna see this now. There is another 2 registers, the load register and the value register. Okay, when we start the counting, we put in the load register some value. Let's call it n, whatever. Okay, and again, this register is also 32 bits. Also, the maximum is we're gonna use only 24 of them. So the other, the rest 8 bits is not used, are not used. Okay, so the maximum count is if 6 Fs. Okay, this is the maximum count. And the last register is the value register, which reflects the current count of the timer. A timer, by the way, is just like a counter, but it's counting based on some time. So if you know the count, you can multiply it by the time per count, then you get a time. It's like a stopwatch, okay? But it's counting down. How this guy is working? When you load it with some value in, it will each count, each clock cycle, it will decrease the this count starting from n until it reaches 0, and all the values or the counted values will be reflected in the var register. If you want to know the current count, you're gonna check the var register. Okay, here is a very simple initialization for it. What else we have here? So here is, for example, you're gonna test or measure the a time for some section in your code, a function, for example. So you record the time before executing this function, then you record the time after executing the function, then you subtract them from each other. And since this counter is counting down, you subtract start from stop. But else also here, here is if you want to make a delay. So one application is to measure a delay, measure execution time for some part in a program. Another application is to create a delay instead of using the for loop, okay, which is really crude way of making a delay because it's not measured. We don't know exactly if we make a count or a for loop from 1 to 1000, how much time exactly it will take. But with this one, this timer, you can implement exact, delay time, 1 second, for example, 900 milliseconds, something like this. Okay, and here is how to make this. Okay, so basically, the timer, when it starts timing, it will count from n to 0. When it reaches 0, the final count, the flag register here, this bit here, the flag, I'm sorry, the flag bit here in the control register will be 1, will turn from 0 to 1. So you know that we reached the end of the counting, okay? Or some time will has been passed. Okay, so this is just an overview for this SysTick timer. I am assuming that you watched the video lecture already. So let's now see the codes that you're gonna implement in this lecture. In the beginning of this lecture, you know, you have another code after half an hour or something. Okay, so this code is actually blinking LED1 each 1 second exactly. We will not do it using for loop like every time we do, but we will do it using exact timer. Okay. So first we make the initialization. We start by the initialization. Okay. And we initialize, Here is we in the initialization, the most important step is to load the control register with 1001. If we go back to the slides. Yes. So in the initialization, we need to enable the timer using this bit. We also need to tie the timer to the source or the microcontroller clock frequency. And we do that by putting also here 1. So these 32 bits, all of them should be 0 except 1 here at bit 0 and 1 here at bit 2. So this will be 1, 0, 1, and the rest is zeros. So if you convert this to decimal, this is just 5, right? So here I am putting 5 in the control register. Actually, this, initializing the load register is not important. So we can even, just, comment this line. It's not really important. Okay. So here is also LED1 initialization. We know LED1 is connected to pin 1.0. So we set it as a GPIO first. Then we put low in it. So the LED will be off in the beginning. It's just initialization. Okay. And now here is the function that will implement the delay. Okay. When we call this function, the execution will be stopped. I mean, will be halted. Okay. And only the timer will, will count until it reaches the time some time. And then we go back to the execution of the remaining program. So let's explore this function. First, you send to this function the maximum number of count that you want to count. And remember, when we count, each count we count is related to is 1 clock cycle. So for example, if the clock cycle is 1 microsecond and the n is 5, then you will count 5 times. So this is 5 microseconds because the clocks, each count take 1 microsecond. So 5 multiplied by 1 microsecond is 5 microseconds. So you could implement an exact delay of 5 microseconds using this function. Okay. We usually start from n-1. Okay. Because we are starting from 1 point to 0. Okay, so we start always from n-1. We also initialize the value register with 0 because we don't know in the beginning what was there. So it's safe to initialize it to 0. Okay. Then I'm creating here a variable. This variable we will read in this variable the current value inside the value register. Because again, the value register is the register that retains, okay, or reflect, or the timer hardware will put the current count in this register. Okay. Then we go to a while loop, okay, and check each time, the value. So first we store the current hello. You guys can hear me?
Yeah, we can.
Yeah, we can.
Yeah.
Sorry for this. So let's go back to the code and the presentation. So I was saying that when the timer is stop counting or reaches 0, this bit here will be 0. I'm sorry, will turn from 0 to 1. So we will know this is our flag. Okay, this is an indication that we finish counting. Okay, starting from n-1 to 0. Okay. So if we go back here to this guy here. Okay. Yeah. So we will only break out of this while loop if control value has this value here. Okay, which reflects every bit in the control.
We can't see your code.
Professor, we can't see your screen.
Okay. Now you can see it.
Yeah.
Okay, so we read here using this operation, this bitwise operation. We read, okay, bit number 16. This bit here. Where is the presentation? Bit number 6, which is the flag register, the flag bit. Okay. So when we reach when the timer is stop counted or reaches 0, this bit will be 1. So this should be the value at that time of the control value variable. And if it reaches this value, if it has this value, then we break, because that means that we reached 0, or we stop the counting or finish counting. Okay. Here is the main program. First, we initialize SysTick. we initialize the LED1 pins. Okay, just to forget about these two numbers now, these two variables now. But let's go for n first. So just to forget about this duty cycle variable. It's just the one. Okay. N now is a variable that reflects the delay. Okay. How to calculate the delay? It's all based on the clock frequency of the microcontroller. Okay. So first, before we go deep and understand this value, why we put this value here, okay, we must know first what is the clock frequency of the microcontroller, okay, and how to know this in this file. This file here, this one that is created, by default, contains the current value of the clock frequency. So let's see what is the current value here. Sorry, yeah, it's the other, this guy, not the other one. Where is it? Yeah, in this file here. Okay, there is a macro here called system clock, which is now 3 megahertz. Okay, you can, of course, it changes its value to any one of these values. So you have the option to run your microcontroller at 1.5 megahertz or 3 megahertz, 12 megahertz, 24 megahertz, or 48 megahertz. The default is 3 megahertz. I'm sorry, the default might be 3 megahertz or 1.5 megahertz. I'm not sure. Okay, but I think it's the default is 3 megahertz. Okay, so whatever. Now we know that the clock frequency is 3 megahertz. Okay, and we want to make or to configure our timer to finish counting after exactly 1 second. Remember, this program is blinking the LED each 1 second. Good. So let's do the math together. I will share the other screen, the tablet, with you, and let's do the math there. Okay. Basically, you guys can see the tablet, right? So if the clock here is 3 megahertz or 3,000 million, or I'm sorry, 3 million hertz. Okay. Good. We know that this is equal to 1 over T. So the clock cycle is something like this. Is the clock, and this is T clock. T clock is equal to 1 over F clock, or F clock is equal to 1 over T clock. Okay. So T clock is equal to, I will leave it like this, 1 over 3 million second. So each count between, so we will count start from some value until we reach 0. Each count will happen with exact time equal to T clock. Good. So one count will happen with time equal to T clock. So how much count, it's unknown, will happen with 1 second. It's proportionality. So, we do the cross here. So N T clock equal to 1 by 1. So N equal to 1 over T clock, 1 over 3 million. It's equal to 3 million. Okay. So that's why n here, if we go back to the code, so that's why n here is equal to 3 million. Because when we pass this value to the timer, we will count 3 million times. And 3 million times is actually exactly 1 second, because we want 1 second. If you want half a second, for example, n will be 1.5 million. Okay. If you want, a quarter of a second, this will be 750,000. Okay, and so on. Always do the math, the proportionality, the same stuff that I did with you, a minute ago. Now, in the while loop, the main program while loop, first you send 1 to the LED, so the LED will be on. Then you wait for 1 second. How to do that? You call this function and send it to it n, because this number is corresponding to a delay of 1 second. Okay, so once we go there, we will go in this while loop, which will only break if the counter or the timer reaches 0, and this will happen after 1 second, exactly 1 second. Okay, good. After this 1 second, you turn off the LED, and again stay for 1 second. Then you go back, turn on the LED, stay for 1 second. Then turn off the LED, stay for 1 second. So you will have the blinking. It's a normal stuff that we do, but we did this before using this dump for loop. We did it like this: for I equal to 0, I less than 1, something like this, some numbers that we don't know how much time exactly this number will reflect, and I plus plus, then do nothing. That's it. Okay, so the program will go into that, million times while loop or whatever this number is, and when I reaches this number, then it will go and but we don't know exactly what is the actual time of this for loop. That's why it's really bad way to do it. But using SysTick, you can do it with whatever time you want. Okay, good. So let me now run it on the kit. And this guy. And I'm gonna show it now. So if you can see, guys, here is a LED is blinking every 1 second. Okay. Now, if I ask the question, okay, let me go back to the screen, to the tablet. So this program, as we said, okay, oh, this guy is not working. Okay. So this program, as we said, will turn on the LED for 1 second. Then it will turn it off for another 1 second. And so on, right? And we know that the LED is connected to B1.0. So if we have an oscilloscope, you know, guys, oscilloscopes, this device that shows signals, you know it?
Yeah.
Good.
Yeah.
So if we put a probe here for the oscilloscope, CRO, if you put the probe at that point here, what we should see? What kind of signal we should see? This signal or something else, you know? You have any imagination?
Yeah, square signal.
Yes, we should see this
Squirrel
signal. We should see, yeah, square wave, that's right, yeah. We should see this signal exactly. I mean, 1 second, 1 second, you know? So I got an oscilloscope from the lab, okay? And I will connect it to this pin 1.0. So I'm gonna show you now how to do that. Okay, so yeah, let me do it first, then so I know that you don't have oscilloscopes, but I just want to convince you more by the SysTick is really working, and we're gonna measure the time. It will be exactly 1 second. Okay. By actual measurements. That's the point from this experiment here, or from showing you that. I mean, you will just code the code. You don't have, of course, oscilloscopes or something. So let me to scale here. Where is this guy? It's completely lost for some reason. Okay. Takes some time to adjust it. And the trigger is here, is battery. The position. Yes. Good. So now I'm gonna show you with my camera here. So basically, you guys can see, right? So basically, this is if you see the jumper here, this jumper beside LED1, it's written beside it B1.1. I'm sorry, B1.0. So this actually, these pins here are connected to B1.0. So I bought my oscilloscope probe at the the metal of this jumper. So it's connected now to B1.0. Okay, and if we look at the screen here, so The voltage per division is 1 volt. So if we measure how many squares, 1, 2, 3, 3.3, and we know that the high voltage of this microcontroller is actually 3.3. Good. Now how about the time? So if you look here, the time per division is 500 millisecond or half a second. So each division on time is around half a second. And it's really hard to measure, but it's actually, so each pulse of those is 2 divisions. So 2 multiplied by 500 millisecond. I'm gonna show you 500 millisecond here. You guys can see it. 500 millisecond.
Yeah, we see it.
Yeah, 500 milliseconds. So 500 multiplied by 2 will give you 1 second. Okay. So of course, this is a proof that we have created a very perfect, not very perfect, but some precise time delay, rather than making for loops or stuff. Okay, guys. So now it's your turn. Just complete this code. Then we're gonna go and use SysTick in another application to control the speed of the motor. Okay, so just finish this first, then we're gonna go and explore another application. Okay. One of the most important application for SysTick or any timer in your processor is what's called the pulse width modulation. Pulse width modulation. So I'm gonna share my screen right now with the other screen. So what is basically pulse width modulation? So pulse width modulation is let me also open up my camera. So if you generated a clock cycle like this or a signal like this, this is a high period, this is a low period. So for example, in the example that we just implemented, this was 1 second and this is also 1 second. For such a kind of signals, we said that the duty cycle is equal to 50%. 50%, which means the high period over the high period plus the low period is equal to 50% or half. Okay. We may have something like this, or we can generate something like this. For example, here this is the high. This is, for example, 1.5 seconds, and this is only half a second. So this is 75% duty cycle. And we can do the opposite. We can do something like this. With 25% duty cycle, or whatever combination you want. We can generate such a signals using SysTick. And we actually did one of them. We did this. The LED was on for 1 second, then off for another 1 second. So let's do, for example, this one. Okay, so I'm gonna share the other screen right now. to show you on the oscilloscope how we can do that. So if we share this guy, okay. That is why I'm using this duty cycle variable. So let's make this duty cycle equal to 2, for example. Okay. So if this equal to 2, then the LED will be on for still 1 second, but then it will be off for n divided by 2, which is 1.5 million, which is half a second. Okay. So expect to see, it's not 75%. I'm sorry, it's not 75%. It's like 2/3 and 1/3. Okay, like 67% and 33%. Okay, so this is just an example for you. It's not I was not doing something exact 75% or 25%. I'm showing you the concept that we can change the duty cycle. So let's now check this on the oscilloscope screen. Yeah. So I'm gonna guys show you now the oscilloscope. So look, the high period is 2/3 the low period. And I am very sorry for this moving signals. Okay. I don't know why it's not static. But anyways, I think it's clear that the high period is 2/3 or double the low period, or the duty cycle is 67%. Okay. So basically, in principle, you can play with this duty cycle variable here to generate whatever duty cycle you want. So, but why this duty cycle thing is important? Okay. First, this is called pulse width modulation. So whatever I'm calling here, so let's first share the other screen. So what I'm doing in here, okay, which is changing the width of, or the duty cycle, is called pulse width modulation, PWM. And the pulse width modulation is a very important concept or technique, and it has many applications. One of them is to control the speed of the motor. Okay, so let's see how. So basically now, if you have a source like this, I have a switch, and you have here your motor. This motor is just a coil, which is a really bad coil here. It's just a coil. So you can just imagine that this motor is just a coil. Okay. One property of the coil is that it can't change its current instantaneously or instantly. Okay. So if you have a battery here, let's say this is a battery, 3.3 volt. Okay, and you have here, for example, some resistor, whatever. Okay, when you close the switch, so in the beginning, before when the switch is open, if we like to draw the current I versus time, so let's assume that before t equal to 0, the switch is closed or open. I'm sorry. So the current is 0. And at t equal to 0, we close the switch. You will not see something like this. No. because the inductor cannot change its current instantly from 0 to something in no time. But it's gradually build up the current. So the current will increase gradually. So the current shape will be something like this. You see, guys? It's gradually building up. And the speed of the motor, is proportional to the current. That means that the speed will be something also like this. You will not see the maximum speed instantly. No, it will rotate, gradually increase the speed until it reaches after some time the maximum speed. Okay.
Hey, Professor.
Yes, Genesis.
Is it cool if you just, whenever you're done, can you go back to the circuit and re-explain that again?
Yeah, of course, now.
Okay, thank you.
So basically, we assume that there is a resistor here, and this is the output of the output, of course, of the micro can be considered as a battery. So you have a battery here, okay, and there is a switch. The switch is open, so the current is 0. And at some time, we will mark this point at t equal to 0. We close the switch. Okay, I'm saying that the current, since the switch is closed, one may think, okay, there will be a current. Yes, there will be a current, but it's not, the current will not go to the desired value that you can calculate using circuits, electric circuit theory, at no time, at 0 time. No, it will take some time to build up. So the current will gradually increase using the green, the green curve here.
Okay, got you. Thanks, Professor.
Okay. And the speed is proportional to the current. So the speed will also gradually increase until it reaches its final value, the full speed. Okay. How we can use this to control the speed of the motor? So this time is called, so the time takes for the current or the speed to reach its 65% of the final value. So this is 65% of this value here. So for example, if this value is 1, this is 0.67. Okay, whatever it is. So if this value is S capital, whatever, speed is equal to S. So this is equal to 7.67 S capital, the final value. Okay. For motors, it's around 100 milliseconds. So this time, it's called tau. For motors, it's around 100 milliseconds. So basically, let's assume you have, a circuit like this. I'm sorry, the signal like this. So this is the signal that comes out of the source. So the microcontroller output is something like this, black signal. This is 3.3. Okay. This is the signal that will feed the motor. The motor speed will be controlled something like this. It's gradually increasing. Okay. Then, and also when the voltage goes to 0, the current or the speed will not go directly to 0 in no time. It will do something like this instead. And again here, will increase. you know, and decrease, and so on. Okay. So you can imagine that the speed is will be correspondent to the average of this red signal. So the speed will be proportional to the average of the red signal, this signal here. How about, and here in that particular case, we have duty cycle equal to 50%. I mean the high is equal to the low. How about if the high is higher and the duty cycle is higher? So how about if you have a signal like this one? Now the speed will be something look like this. And it has enough time to reach the fall. Then when it decreases, it will not go to zero like this one. And so on. Now I'm asking you the question. Does the average value of this signal here larger or equal or smaller than the average value of this signal? So this is signal 1, this is signal 2. So average of signal, this is 1, this is 2. Average of 2 is larger, smaller, equal to the average of 1. Any idea?
Average 2 is greater than average 1.
Yes, of course. So average 2 will actually be greater than average 1. So speed 2, the speed in the case, the speed of the motor in case 2 is larger than the speed of the motor in case 1. Okay. If we take another example, the third one, in which I will do the opposite. Maybe here. And the response of the motor this is number 3. Now average 3 is less than average 1, and of course average 2. So the speed in the third case is less than the speed of the case 1, and of course the speed in the case 2. Okay, because the duty cycle here is equal to 25%. Here the duty cycle is 75%, and finally this one, the duty cycle is 50%. Okay, and we're gonna do that using SysTick timer. So let's go to the code now, to my code that I'm controlling the motor from, or using whatever you call it. So motor speed SysTick. Okay, so again, the initialization. We don't need LED1, by the way, here. I just forgot to omit it. Yeah, we don't need it. So sorry for that. Sorry for that. So we know the initialization. We know this is a delay. Okay. Here is the motor driver initialization. You remember that guy, okay, from last week. So we have first what's the sleep signal, in which we put 0 in order to, I'm sorry, put 1 in order to not to the motor to, in order to wake up the motor or make it, rotate. If we put 0, it will stop. Okay. So this setup for the right motor, the right wheel, and this setup for the left wheel. Okay. You remember, guys, there was a bin called PWM bin. So if we, I'm not sure if I have this or not. No, not this one. Oh, it was here. Yeah, sorry. It was here all the time. So here is, the driver chip. Okay, you have here is a phase in which 1 means backward, 0 means forward. And you have here what's called the enable. And you see, guys, it's called PWM lift. So this is the chip for the lift motor, by the way. Okay. Here we control the direction. 1 means backward, 0 means forward. And here, last time we put just 1 here. And when I said it's full speed. Okay. So basically, if you don't feed it with all the time 1, you feed it with something like a square wave with it changing the duty cycle, you can change the speed of the motor. So we're gonna use this bin, but this time we're gonna feed it with a variable duty cycle signal. So we can change the speed. If we put just 1, the motor will move all the time with its full speed. Okay, so let's see what we're gonna do. So this is the initialization part of the motor. I know you guys know that already. You can just copy and paste. Okay, SysTick initialization, motor driver initialization, some variables. Okay, so what we need here, I'm gonna run the motor with different duty cycles. Okay, but the whole period is 10 milliseconds. So the period, the high and the low, both high and the low is 10 milliseconds. Okay, and 10 milliseconds means the number of counts is 30,000. Okay, you can just do the math. If it's 3 million, it will be 1 second. If it's 30, okay. Sorry, guys. The internet is very bad. Okay. Okay, let's continue. So first, I will run, forward for 5 seconds. So this is the application that I will do. I will change the speed, and for each different speed, I will run the motor for 5 seconds. Okay. So first, full speed. Full speed means that the duty cycle is 100%, or the low time is 0, or the signal is just high, just DC. Okay. So for this reason, I just put the high cycle is equal to the full period.
Professor, you're not sharing your screen.
I'm sorry. So I'm saying that you guys can see the code right now. You can see
Yeah,
the
we
code?
can.
Good. So what I'm saying is that for each different speed, I will run the motor for 5 seconds. Okay. Good. So first, for full speed, that means the signal is all high. The duty cycle is 100%. Okay. So that means the low period is 0. So that's easy. That's the normal thing that we did all the time. Okay. And remember, we want to do it for 5 seconds, but the delay here is only 10 milliseconds. So 10 multiplied by 500 will give you 5,000 milliseconds, which is 5 seconds. So I did here a for loop. Okay, in this for loop, I put high on 2.6 the right wheel, 2.7 the left wheel, and the delay is high is 30,000, which is 10 milliseconds. And since I will do that 500 times, so it's just 5,000 milliseconds, which is 5 seconds. Good. Then I will stop the motor completely for 5 seconds. Okay, so this should be not 5 seconds. This is 5 seconds. No, this is not 5 seconds. So here, put 500 as well. Okay, so 500 and yeah, I'm sorry. Yeah, good. So 1 second, because I changed the variable. 1 second cycle is a variable which has 3 million. So this is corresponding to 1 second. So here just loop 5 times, and each time you delay 1 second, so it's 5 seconds. And I just put low here on 2.6 and 2.7, so the motor should stop. Good. The second speed we're going to test our motor with is the speed at which we have 75 duty cycle, or 75 of the full speed. So I will run the motor for 0.7 period cycle, 0.7 multiplied by 30,000, and the low cycle is 25% or 25.25 multiplied by 30,000, which is the full period. This will give you 75% duty cycle, and this will decrease the speed a little bit, or by quarter. Yeah. This is 3/4 of the full speed, we can say. Then again, I will put high on the I'll put high for high cycles, then put low for low cycles on the motor PWM signal, which is 2.6 and 2.7. That's why the speed will decrease a little bit. Okay. Then I will stop again for 5 seconds. Then the third speed is the speed at which we have 50% full duty cycle. So the high cycle is equal to half multiplied by the period cycles. and the low cycles again is 0.5 or half the period of the 30,000. Okay, so for 500 times I will run with I will put high on 2.6 and 2.7 for high cycles, a number of cycles called the high cycles, which corresponding to have 5 milliseconds. Then I will put low for another 5 milliseconds. Remember, again, the total is 10 milliseconds. And I will repeat this for 500 times. So, I'm sorry, this is 10. This is 5, actually, I'm sorry. Because I'm just making copy and paste. So, yeah. So the total will be 5,000 milliseconds, which is 5 seconds. And again, here I should do that 7.5 milliseconds, and here is 2.5 milliseconds. Good. Then I will stop again for 5 seconds. And lastly, the last speed is the lowest speed. Of course, you can go to 0, but this is I'm saying is lowest speed in that program, which is a quarter of the full speed. So 25%, the duty cycle is 25%, means the high is 25%, which is 2.5 milliseconds, and the low period is 75%, which is 7.5 milliseconds. Okay, so this is 2.5 millisecond, and this is 7.5 millisecond. Oops. Something wrong. Yes. Okay. And again, stop for 5 seconds. So let me share the motor with you. I'll remove this first. Okay. I'm not sure if you can see it quite well. Okay, so now I'm gonna run it. I want you to observe the speed, that's changing in speed. So first, this is not on, so make it on first, that's important. This is the full speed. 5 seconds. Stop, then 75% of the full speed. 5 seconds stop. Then half of the full speed. 5 seconds stop. Then the lowest speed. Okay. But remember here, the battery, my battery is, you know, is a little bit low. That's why even the full speed is not the real full speed. If your batteries is good, it will run faster. Okay, so it's always proportional to the full speed, whatever it is. Okay. And I put here in the program, I put here a break. It's not an infinite loop. I put a break here just to not to drain out your battery. Okay. So guys, I will share a screen for a moment for you to take photos of this guy. Okay. Actually, you have this, just copy and paste. You